Today we are going to discuss the Faraday's law. After discussing the electrostatics and magnetostatics, where the electrostatics deals with the field produced by the stationary charge, and the magnetostatics, as we have discussed in previous sessions, like a moving charge can produce a field surrounding any conductor, so which will be like in circular fashion or a loop fashion, so that we have discussed. But when we take in real-time scenario, apart from electrostatics and magnetostatics by dealing separately, instead of that, so how a wave can be traveled if suppose, for example, I can explain like, if you take mobile communication from the base station, the mobile can receive a signal. How the mobile can receive a signal? In form of a wave. The signal will be in the form of a wave. What type of wave it is? The wave usually consists of, as we know that it is a electromagnetic wave. Till now we have discussed electrostatics separately, magnetostatics separately, or electric field separately, and magnetic field separately. Now we are going to discuss how exactly the wave carries these two fields, how these two fields vary with respect to time. For example, if you take an antenna, if I say an antenna like this, an antenna, so I'll write an antenna, simply an antenna starts radiating a signal. So the signal will be like this. This is, we can say, a simple sinusoidal wave where a two-dimensional wave will be there. But so now we have to write in terms of axis, if you see. So that is what we have studied in coordinate systems. So this is x-axis, if you say, and this is y-axis. And when you consider this as z-axis, the three coordinate system or rectangular coordinate system where all the three axes will be perpendicular to each other or orthogonal to each other, then one of the axes represent, for example, here we can say electric field, and this represents magnetic field. And if you see the z, why we require z here is to represent the direction of propagation of wave. How this direction of propagation of wave takes place, like, so we will write like this. So this is the direction of propagation of wave. At the same time, so we'll be having, this is what we'll get. That means we will be having three-dimensional structure to analyze any electromagnetic wave. So that is why this electromagnetic wave will be varying with respect to time. Till now we have not discussed. Only we have discussed because of a stationary charge, what is the field generated, or because of the moving charge, what is the field generated. Now, how the field varies with respect to time, as the wave travels from source to destination in space, definitely it will vary with respect to time. So all these things can be represented by different types of equations. These equations were proposed by Maxwell, and it was demonstrated by Hertz. So these are the things which we are going to discuss in this particular module. So first we will take up Faraday's law. Let us see here one by one each and every Maxwell's equation we are going to derive here. First we will see an EMF, that is electromotive force, induced in a closed path. Let us take a closed path like this. An EMF will be induced, maybe as conductor will be there. So the moment of charge, or we can say current, will be like this. So here there will be H, that is the magnetic field is produced like this. Okay. So now the EMF induced in a closed path on closed circuit is equal to the rate of change of magnetic flux. We know that the magnetic flux will be represented by phi, the rate of change of magnetic flux here. So magnetic flux enclosed by the closed path. Everything is related to closed path only. Now the EMF is induced, that is what we can say. So this will be the rate of change of flux, means d phi by dt with respect to time. It is varying, but it is equal to, we have mentioned it as EMF, that is electromotive force. So if you see the equation here, it is represented as negative sign. The rate of change of flux with respect to time is with negative sign. Why the negative? What is the significance of negative sign here is, the negative sign indicates that the voltage induced or voltage acts to produce an opposing flux. The voltage which is induced in the circuit which can oppose the flux, so that opposition will be given by the negative signal, the negative sign here. This is called as Lenz's law. Already we have discussed these things in physics itself. When the induced voltage which opposes the flux in a closed path is called as Lenz's law, right? So according to that, if you see, if suppose instead of only one path, if the same path is having n number of terms here, n number of terms here, then your EMF will be equal to minus of, that is negative sign, n into d phi by dt. d phi by dt, right? Because of n number of turns. Next, so now d phi by dt, if it is a non-zero value, what are the two conditions we have to see here? There are two conditions to make it as d phi by dt, that is varying flux with respect to time. If it has to be non-zero, so then there should be two conditions. What are the two conditions here is, either one time the flux should be varied, the phi will be varying, but for a stationary path. The closed path, whatever we have here, it should be stationary and the flux should be varied. This is the first condition. The second condition is, or the closed path is moving like this with some velocity, but the flux is constant. These are the two cases to make d phi by dt non-variable or non-zero value here. And the third combination is both of them. Both can be moving or both can be stationary, right? So now what exactly induced EMF will be there means, E is equals to, let us write, E is equals to closed loop integral of, or closed line integral of, we can say E dot dl. What is E dot dl here? So earlier we have discussed what is E dot dl is. The closed line integral of E dot dl is nothing but potential V, or it also can be represented as E. That is why E is equals to closed loop integral of, we can say L, closed loop integral of E, closed line integral of E dot dl here, right? So this is your EMF, induced EMF here. Just a minute. Now the induced EMF will be is equals to, so let us write here, E is equals to minus d phi by dt. We know this, minus d phi by dt. But what is phi? Phi is also is equals to integration of b dot ds. What is b here? The flux density. B is flux density, because we are using here flux density means flux per unit surface area. Now we are calculating the flux throughout the surface area. That is why we have to take surface integral here. The surface integral of B dot ds. ds is a small incremental surface area here. So phi is equals to surface integral of B dot ds. Let us substitute this in the above equation. We will get here. So E is equals to minus d by dt of, okay, substitute this surface integral of b dot ds here, right? So let us take the derivative inside, the surface integral of, with the negative sign here, so minus dou b by dou t dot ds, minus dou b by dou t dot ds here, right? So instead of flux, we have converted the flux in terms of flux density here. Variation of flux density with respect to time we have considered here as dou phi here. So dou phi by dou t. You will get the EMF equation as E is equals to minus surface integral of minus dou b by dou t with dot ds, that is incremental surface area here, right? So now based on the EMF induced in a closed path, we have discussed two conditions. One is flux is varying but the stationary closed path. Another one is flux is stationary but the path will be moving. Let us consider the first case where the flux density is varying and a stationary closed path here. So this is what we can see. Flux is varying here but stationary closed path. This is called as transformer EMF, transformer electromotive force. So the same thing we have discussed here. There is a closed path which is stationary, but the flux is varying with respect to time. Then the induced EMF is statically induced EMF will be given by closed loop integral of E dot dl. E dot dl. So that will be is equals to surface integral of minus dou b by dou t dot ds here, right? So now if you see the same equation whatever we have here, so that is E dot dl equal to minus dou b by dou t dot ds. So now, so if you see the LHS here we have line integral, RHS we have surface integral. We have to convert either both to line integral or both to surface integral. We have an equation, so that is by using a Stokes theorem, what we can do is the line integral can be converted into surface integral. Line integral can be converted into surface integral. Based on that, so the above equation can be written as, if you see here, so that is surface integral of del cross E, that is curl of E dot ds will be is equals to surface integral of minus dou b by dou t dot ds. Now if you see the LHS and RHS both will be surface integrals only. Surface integrals only. Now we can equate the equate LHS equal to RHS because both are surface integral. Now if you remove these integrals, what is the other condition? ds is common, surface integrals are common, therefore we can say del cross E, that is curl of E will be is equals to minus dou b by dou t. Minus dou b by dou t. So this is called as one of the Maxwell's equation. This is one of the Maxwell's equation. So here what is happening here? B is varying, that is the flux is varying, but for a stationary path we have found this. This is usually derived from Faraday's law. What Faraday's law says that E is equals to E dot dl. From that we have derived this equation. So finally E is equals to minus dou b by dou t dot ds. So E dot dl is equals to minus dou b by dou dot t. Line integral has been converted into surface integral using Stokes theorem. Finally we have got del cross E is equals to minus dou b by dou t. This is one of the Maxwell's equation which is derived from Faraday's law. Let us see the second case. The case is generator EMF. Generator EMF, as we have discussed earlier, the second case is the path will be moving, but the stationary flux here. For a stationary flux, but the path will be moving. That is why you have written here static B and moving closed path. Static B, moving closed path. Now, if the path is moving means there should be a velocity associated with it. So that is why we have to consider here. Consider a charge Q moving in a magnetic field with velocity V. The force exerted on Q is F is equals to. Now let us consider the force F is equals to. So here Q, okay, velocity V cross B here. The path is moving, because of that we will get velocity here, and B is fixed, so that is why we have written here, right? So now we know that let us take Q to LHS. It will become F by Q will be is equals to V cross B. V cross B. We know that force per unit charge is electric field intensity. We know that force per unit charge is electric field intensity. Now, what type of electric field intensity? It is motional electric field intensity, because the path is moving. When the path is moving, it is motional electric field intensity. That can be represented by EM. EM is equals to, okay, V cross B. V cross B. It is also is equals to the force per charge. The force per charge here. So this is EM. So we can say electric field intensity is equals to force per charge here. Now the induced EMF, already we know that induced EMF is equals to line integral of EM dot dl with line integral here. So let us substitute the same here. So what is EM here? V cross B, that is equals to integration of V cross B dot dl. So put the bracket here, dot dl. So this is about the equation here. If B is time varying, and closed path in moving, the total EMF will be the total EMF. Now we have considered two types of EMF. One is transformer EMF, where we have got del cross E equal to minus dou B by dou T, and generator EMF, where we have considered E is equals to V cross B plus dl. Then what is total EMF here? Let us write. Total EMF will be given by, so integration of E dot dl will be is equals to surface integral of minus dou B by dou T plus dot ds plus closed line integral of V cross B dot dl. So this is the total induced EMF we will get from this thing, right? Now we have discussed two types of EMF. First is how induced EMF will be how induced EMF you will get from are contributed for a variation of flux with respect to time, that is variable flux with respect to time. ಇದನ್ನ ಕಟ್ ಮಾಡ್ಕೊಳ್ಳಿ ಈಗಿಂದ ಮಾಡೋದು. Okay. So we have discussed EMF and two types of EMFs. One is transformer and generator EMF. Let us move on to the displacement current and current density. So we have seen from Faraday's law, del cross E is equals to minus dou B by dou T. For a steady magnetic field using Ampere circuital law, we know that del cross H is equals to J. That is curl of magnetic field intensity. Curl of magnetic field intensity is equal to current density. Is equals to current density. This is called as Ampere circuital law. In magnetostatics, we have discussed this and we have derived the equation del cross H is equals to J here. Now we will see how exactly this will be varied, or with respect to time, how exactly this can be introduced, like how the with variation of along with the time, how these parameters will be varied here, or magnetic field will be varied, or current density will be varied, right? So now let us take divergence on both sides. Del dot of del cross H will be is equals to del dot J here. But the LHS whatever we have, divergence of a curl will always be equal to 0. This term will be 0. Divergence of a curl is always is equals to 0. Therefore del dot J is also equal to 0. Therefore del dot J is also equal to 0. However, but del dot J using current continuity equation we have written like, so del dot J will be is equals to minus dou rho V by dou T. That is del dot J, divergence of current density will be is equals to, with negative sign, the variation of volume charge density with respect to time, right? So now del dot J with respect to the previous case, if you see, our divergence of a curl is equals to 0 because of the divergence of current density is also equal to 0. But if you say by using this equation, if this term, this RHS, if it is 0, then only del dot J is also 0. If RHS whatever we have written here minus dou rho V by dou T, if it is 0, then only this will also be 0. But we cannot consider for time varying fields there should be a modification, because this cannot be 0 easily. So that is why, though we have to modify this Ampere circuital law, that is why we are doing the entire derivation of this modify current density as well as displacement current density. Right. So now what we are going to do here is, for Ampere circuital law, if it is Ampere circuital law only, if you apply the divergence, you will get 0. But we should not get 0 because minus dou rho v by dou t cannot be saved. Now what we have to do is, so let us say del cross H is equals to J according to Ampere circuital law, but we are going to introduce one more parameter or some constant here that we can consider it as n here, n cap. That is a constant vector we can consider here. Now what we have to do is apply divergence for this. So del cross H will be is equals to del dot J plus del dot n. Del dot J plus del dot n. So curl of a divergence of a curl or del dot J is equals to 0, we have seen because of the previous case. When this RHS will be 0, when this RHS will be 0 means when del dot n will be is equals to dou rho v by dou t. If this condition is satisfied, then RHS will be equal to 0 in the previous equation. Why? Because del dot J is, what is the value we have given? Minus dou rho v by dou t. If minus dou rho v by dou t, if del dot n is dou rho v by dou t, then you will get RHS as 0 here, right? So now what we have to do is here, since del dot J is equals to minus dou rho v by dou t, and we know that del dot D is equals to rho v. What is that? Del dot D is equals to rho v. The del dot D equal to rho v means point form of Gauss law we can say, or we can consider it as del dot D is equals to rho v. The divergence of electric flux density is equals to volume charge density. Maxwell's first equation with respect to electric field. Maxwell's first equation, del dot D is equals to rho v here, right? So now because of this, what we can write here is, so del dot n, let us take the equation, is equals to, right? So dou rho v by dou t, that is also is equals to dou rho v by dou t. Substitute for rho v here, dou by dou t of, what is rho v here from the previous equation? Del dot D here. So then that is also is equals to del, we can take it out, del dot dou d by dou t. What is that exactly? LHS, let us write del dot n cap. Del dot n cap is equal to del dot dou d by dou t here. Now if you see what exactly we have found here, n cap is equals to dou d by dou t. Earlier we have considered del dot n cap is equals to dou rho v by dou t to make this 0. But now after substitution of del dot d equal to rho v, or instead of rho v we have substituted del dot d. Now del dot n equal to del dot dou d by dou t. So it implies that, so now we can write n cap is equal to dou d by dou t. Let us consider now the equation here. So what's the equation we have? This is the equation. Now the equation we can consider del cross H is equals to J plus n, that is what we have considered. If you see there, J plus n. So now del cross H is equals to, let us retain J here, plus what is n here? N we have derived as dou d by dou t. That is also is equals to J C plus J D will be is equals to del cross H. Curl of a magnetic field intensity we have modified. Earlier it was del cross H is equals to J. Now after finding the value for a constant by modifying the equation, n cap is equals to dou d by dou t. Now del cross H is equals to J plus dou d by dou t. First J whatever we have considered here is JC, that is conduction current density, and the second JD, that is second term in the RHS, will be considered as displacement current density. This is called as displacement current density. So now that is what exactly we have done, displacement current and displacement current density. Current density, Ampere circuital law, whatever we have derived in magnetostatics was only del cross H is equals to J. Now here for time varying fields what we have done is, so displacement with respect to time or displacement current density with respect to time, that we have included into the equation of Ampere circuital law by modifying the equation. So we have got del cross H is equals to JC plus JD. JC is nothing but current density or conductor density, and JD is displacement current density. So this is how exactly we have modified the Ampere circuital law. Thank you.